To be here and give a seminar here. Very nice to be at KAIST. So I'm going to talk about powers of 2 in modular degrees of modular abelian varieties. Can you hear me actually? Mic is working? Okay. Let E be an elliptic curve over Q. Then by modularity of elliptic curves, there exists a surjective morphism from the modular curve x naught of n to E. I will define what is x naught of n. X naught of n is the modular curve, and if you consider the 2 by 2 matrices with the determinant 1, then it acts on the upper half plane. Those with the imaginary part of Z, imaginary part is strictly greater than 0. SL2 of Z acts on H. The action is defined by ABCD AZ plus B by CZ plus D not equal to 0 minus D by C infinity. Z is minus D by C. We can extend this action to Q union infinity dn that is M by n. Zero and not equals to 0. Yeah, so I have defined an action SL2 of Z acting on H and then Q union infinity, and if I consider the subgroup gamma 0 of n, which is a subgroup of SL2 of Z defined by all ABCD such that C is congruent to 0 mod n and AD minus BC equals 1. If I consider this subgroup gamma 0 of n, we can restrict that action to this subgroup. So gamma 0 of n acts on H union Q union infinity, and I can consider the orbit space infinity. This is a compact Riemann surface. If I consider all together the set of points, these points, they are called cusps, and this point points of Riemann surface. If we consider only gamma 0 of n orbit space for this one, then this is not compact. If I adjoin the cusp, then it becomes a compact Riemann surface, and this I am denoting the modular curve x naught of n. So by modularity of elliptic curves, there is a surjective morphism from x naught of n to E.
Your n should be the conductor on there.
Yeah, thanks. Actually this morphism is not unique, and we can change n also, but for the time being we are taking n to be the conductor. There is at least one morphism from x naught of n to E. There may be several ones, but yeah. And if this morphism factors through another elliptic curve, suppose for example x naught of n to e prime to e, then the degree of this one and the degree of this one will be multiplied, and this is multiplication by degree of 2. So I am considering the optimal elliptic curve which is not factoring through any other elliptic curve, that optimal map, degree of that optimal map. Isogeny class, choose E in its isogeny class such that minimal degree. So it won't factor through any other elliptic curve. That minimal degree is called the modular degree of E. So Watkins conjecture let E over Q be an elliptic curve with conductor N. And the rank R, then 2 to the power R divides modular degree of E. So 2 to the power R divides modular degree of E. This is Watkins conjecture, and my supervisor he proved this conjecture not for all elliptic curves, for certain category of a large category of elliptic curves, assuming some conditions on the elliptic curve. For example, he assumed there is no two torsion point on E. There is no E of 2. There is no rational two torsion point. This is empty set. This is one assumption. So this kind of assumption, he assumed several conditions, 4 or 5 assumptions on E, and he proved Watkins conjecture. And also one assumption, one big assumption. Maybe I will write just. So he assumed some conditions on E. For example, one of that condition is rational two. There is no rational two torsion points, and some more conditions. And also he assumed some R is isomorphic to T result. When I give the sketch of the proof, you can see what is R is the universal deformation ring, and T is the completion of some Hecke ring coming into the picture. Even when Wiles proved the Fermat's last theorem, for semi-stable elliptic curves, he wanted to attack this R is isomorphic to T conjecture, and he proved this one is true for semi-stable elliptic curves, and he proved the Fermat's last theorem. Yeah. So he assumed R is isomorphic to T. Still we don't know whether this is true or not. Still my supervisor and myself, we don't know whether this is going to be true or not. Okay. My thesis problem. My thesis. W, let W be the group of Atkin-Legner involutions. This is certain matrices WD matrices. just, and cardinality of the Atkin-Legner group, that is nothing but 2 to the power s, where s is the number of distinct prime factors of n. Yeah. So this Atkin-Legner group, it acts on x naught of n, and we have the modular degree and the surjective morphism from x naught of n to e, that is phi, and w acts on x naught of n. Now I can define one subgroup of the w prime inside w. This is defined by all w in w such that equal to phi. So by definition of w prime, we can see there is a quotient curve. There is a modular curve x naught of n, and there is a quotient curve x naught of n over w prime to e by the definition of w prime. And the degree of this one, x naught of n to the quotient curve x naught of n over w prime, the degree is nothing but cardinality of w prime. Now Watkins conjecture, it says 2 to the power r divides the whole degree of phi. And we can ask whether 2 to the power r divides this portion, means 2 to the power r. If I denote this one to be phi prime, then I can ask p prime. Yeah. So in my thesis, myself and my supervisor, we proved assuming the same conditions on E and same assumption R is isomorphic to T, the stronger result 2 to the power R plus K divides degree of phi. We improved the bound 2 to the power R by some more factor 2 to the power K. And we can ask another question. For modular abelian varieties. In the elliptic curve case, we had the modular curve and then morphism from the modular curve to the elliptic curve. But when we consider modular abelian varieties, there is no such morphism from the modular curve to the abelian variety. But we do have a map from the Jacobian J naught of n. If I consider A is a modular abelian variety, there is no such morphism from x naught of n to A, but there is a morphism from J naught of n to A. Now if I consider the dual A dual to n, then there is a theorem, it says the degree will be some square. Degree of this isogeny will be a square. So I am defining.
Well, in your abelian variety, still assume that the abelian variety is defined over the rational numbers.
Yes, I should say like A is a modular abelian variety defined over some number field K. A is a number field here, because when I attach a modular abelian variety, so I can attach one cusp form a n q to the power n, a n of f I can say, and if I consider the a n of f, this is a number field, so this is where that modular abelian variety is defined.
F is a cusp form.
Yes, it's a cusp form, new form, yes. We should write so we have j naught of n to a, and I am considering the dual one phi tilde, maybe if I denote this one phi, this is phi dual. Yeah, so the composition that will be some square, and I am considering, I am denoting modular degree of equal to square root of and this definition and the elliptic curve definition that matches, because in elliptic curve case we had x naught of n to e, and if I consider the dual of the whole map, then that is E dual yeah. So E dual, that is isomorphic to E in elliptical case, and the composition will be multiplication by degree of phi. And multiplication by degree of phi, degree of this map, this is nothing but degree of phi the whole squared. So if I take the square root, it matches with the abelian varieties case also, the definition matches with the abelian varieties case. So I will just write down the main result and try to give the sketch of that main result, okay. There is no rational two torsion point, that also I am assuming, and then A of R, the real points, is connected. Coordinate of component group every. Here I should write what is phi of A comma A means group of components of the special fiber of the Néron model of the abelian variety. So I am assuming that condition, and then fifth condition I am assuming two doesn't divide discriminant of OF. So A is attached with a new form. So OF I mean is it of A and of F? So 2 doesn't divide discriminant of OF. Two to the power R minus D modular degree of A. And I will I'm also assuming the same condition, R is isomorphic to T, assuming to D, and I should write K equals K of, that is Q of A n of F, number field where the abelian variety is defined, and D is the dimension of A, which is equals index of K, OQ. D and
box mean?
Yeah, box means. Yes, so there is some number, bit complicated. I will write it down maybe. And G, consider all G such that G is a new form and eigenvalues of G that is AP of G lie in an unramified extension of Q2 and AP of G F2 bar. If we consider AP of G and then AP of F, they are same in F2 bar.
So in your new form, you don't care the weight of the new form. Whatever weight you have, it doesn't matter.
We are considering weight 2 only. Maybe I should mention that also.
Weight 2.
Yeah. And define the vector nu of G for every P dividing N. You see W of G minus W P of F, they are plus or minus 1. So if I consider that vectors in F2, this is 1 they are because plus or minus 1. So if they differ, so then it is 1. If they are equals, then it is 0. That I am considering for every P dividing N, and B is the matrix with rows nu of G. And K is rank of B, and this box going to be if I consider OK tensor with Z2, OK is the algebraic integers in the number field k, and if I consider the tensor product, then I can write it down as O lambda I equals 1 to I, O lambda I so I should write I assume 2 is unramified, so I don't have the index EI here. I have only product of distinct primes, and this O lambda is just inverse limit of okay. So this box now, okay, I have all those things k and all those things. So this box is nothing but summation lambda. So it's a bit complicated, so that's why I left a box there. And this is one result, and also another result we have got like 2 to the power r minus d times cardinality of w prime power d. So this also divides modular degree of A. When cardinality of w prime, that is greater than or equal to, when it is non-trivial, then it's at least going to be 2, because cardinality of w prime is power of 2. So if it's non-trivial, then it's going to be power of 2. So if I combine these two, then 2 to the power r divides modular degree of A. That is the analog of Watkins conjecture in the modular abelian variety case. So we had obtained this result and we had obtained this result. I will give a sketch.
I'm wondering that in the first assumption, if n is odd, what happens?
If
And you start from the fact that n is even.
n is even, we want to.
What happens if n is odd?
Actually, they had computed several papers, recent papers. They had explicitly they had given what will be the powers of all the primes in odd modular degrees by the work of Ribert, Stein and Agaste. All those people, they worked out for what happens when odd modular degree. And when n is also odd, conductor odd, and then modular degree is odd, all those things they worked out in the recent papers. So we are considering only the case when n is even. So as I said, 2 is unramified, so 2 OK. And OK tensor Z2. And this is also isomorphic to OF tensor Z2. And T2 of A, the two-adic Tate module, that is nothing but inverse limit of all the power of 2 to the power n torsion points. And V2 of A Z2 over Q2. Now I am going to introduce one notation. If M is an for an OF tensor with Z2 module M, this one I am going to denote is like the projection EIFM. EIFM is a module over OF tensor with Z2. Then I can project it to the O lambda I, and then so I am calling the tensor product with O lambda I to be EIM. Let T lambda IFA, this is the ith projection of the Tate module. This is a free module of rank 2. Rank 2 and V lambda IFA. This is a vector space K lambda I vector space of dimension 2. And I am considering Vi. This is F lambda I. Dimension 2. So for every I we have a Galois representation. So we have the Galois representation, and because T lambda I is a O lambda I module of rank 2, I will have a rho I from rho I bar, it's a reduction modulo lambda I. Now, because we assume 2 is unramified, this is also nothing but EI of the two torsion points AF2. Okay. Let Vi star as usual all homomorphism for F2 and Wi be a symmetric square of Vi and W I will define the Selmer group. Selmer group, this is Wi, such that when we restrict to Galois group of QP bar over Q, that is inside LP for every P less than or equal to infinity. For every P dividing N, LP is kernel of, oh sorry, Wi power 0, Wi power 0, this is one generated with only one element extensor X. GP, I mean the Galois group of QP bar over Q. IP. So this is the Selmer group. So by using Tate's local duality theorems, cardinality of d prime of Q comma Wi, this is greater than or equal to times multiplied by 2 to the power fi, which is 0. So we applied Tate's local duality theorem and we computed cardinality of this Selmer group, that is turns out to be greater than or equal to. This is a dual Selmer group exactly defined in the similar way, considering the dual of LP. In the place of LP we are considering dual of LP, and so we can compare the cardinality of the dual Selmer group and Selmer group with the factor multiplied by 2 to the power fi. Fi is the degree of the prime lambda I. Okay. And we have the descent map psi this is injective. We have this map. This is just if I take a point P, then this will go to like minus P. This goes to this class. So we have that descent map. If I take EI, this is an injective map, and if I take the projection, then EI of this is isomorphic to H1 of Vi star, and I have a squaring map S from Vi star to Wi star, and I can consider the induced map in the cohomology group. So I have the map S star induced map Wi star. So psi I. Yes. The kernel of this composition, it has a size. Kernel has size. This is the extra factor. The kernel of this composition map is 2 to the power fi by cardinality of H0 of Q of Wi star. This is the extra factor appearing in here. That is the extra factor appearing in here. Yeah, so by kernel of, I should say kernel of S star. Oh, sorry, kernel of composition map psi I composite S star. The kernel of the whole map. And because this is injective and this is isomorphism, yeah, so the coordinate of the image, so where the image will be landing in, image we computed explicitly what is the image. So I know it will be landing in here, but even more precisely it is landing inside the subgroup we defined with the Selmer group with LP perp. So it is landing in the dual Selmer group, that is more important here. The image of the composition map, that is landing inside the dual Selmer group here. So I can write the image. Star. And kernel of this one and this one multiplied by that one, so I can conclude cardinality of FIR. Okay, now 5 more minutes I will define category. The C is the category of complete Noetherian local rings. Rho bar from Galois group of Q bar over Q to GL2 of F lambda phi. It is said to be of type D. If rho is unramified. Outside N, and rho restricted to the decomposition group GP, that is of this form omega chi inverse star 0 chi for some non-zero star, and omega is the two-adic cyclotemic character. And chi is a unramified character sending Frobenius element to AP, and determinant of rho is the two-adic cyclotemic character omega. So all these conditions are deformation conditioned by the theory of Mazur's theory. It tells all these conditions are deformation conditions, so there will be a universal deformation ring RD. Deformation ring. What is universal deformation ring means? We have one morphism, one Galois representation from Galois group of Q bar over Q to GL2 of RD, such that suppose any other representation rho from R, this is in our category, and rho is of type D, then it factors through RD. That is what universal deformation ring. If any representation of type D, then it factors through RD. Okay, so RD universal deformation ring exists. I am calling the Galois representation associated with that one, rho D of universal one. And recall, I defined Vi, lambda I, Ti, T lambda I, and Tate module and everything. So for every I in the decomposition 2OK decomposition ring, for every I we have one Galois representation from Galois group of Q bar over Q to GL2 of O lambda I. These representations we can check, these all type D. So we have one map from RD to O lambda I. Because this is of type D. If I denote kernel of phi R to be this one, then I can't write each and everything explicitly, so we have phi R, that is kernel of phi R because of type D. And what I want to say is we can relate the cardinality of the Selmer group d prime of q comma wi with this we can relate the coordinate of this and this, and we have 2 to the power fi ri appearing in here. This is greater than or equal to 2 to the power fi ri, and this one, because we can relate these two, and while going from here to there I can relate that ki, what I defined the rank of the matrix bi, I can come up with the extra factor in here. So 2 to the power ri fi divides this one, I can come up with 2 to the power ri fi divides this one, and summation, when I take the summation for all I, then summation of fi ki is that box 1, and summation of fi ri, that is the rank, and summation of small ri, that is the dimension d. Sorry, here fi. So this is the dimension d. So I can conclude 2 to the power r minus d plus that box divides, and for the second result, for this result, what we do is we fix that f q to power n, and we consider one Heckering T that is generated by TPs and WPs. WPs are Arkin-Legner involution, and OF, I can say OF. WPFF. I consider psi f is this map, and kernel is a maximal ideal, kernel of psi f maximal ideal, and the Heckering completion of the Heckering with respect to that maximal ideal Tm, that is isomorphic to product of OG this is isomorphic to product of OG, G is a new form such that WPF G equals G, and similarly I have one type D prime, and also I have the universal deformation ring RD and to Tm, because when I consider the each projection to OG, that rho G from Galois group of Q bar over Q to OG, this is of type D. When I put together, then the rho G to product of rho G from Galois group of Q to this is type D. So I have the map from RD to Tm. There I can plug that extra factor, coordinate of that Arkin-Legner involution factor while comparing the degree and everything. This is a sketch actually. There are so many steps involved. Just I am quoting down what we do for that second result. For second result, similarly we defined one universal deformation ring and then compute the coordinate and everything. Yeah, and I want to say one more thing. We have used magma and sage, and we had come up with hundreds and hundreds examples of abelian varieties, modular abelian varieties, satisfying all those assumptions I defined. A of R is connected, N is even and square free, and there is no rational two torsion point, and all those conditions, 5 conditions in the beginning, all those conditions are satisfied for those hundreds and hundreds of examples. And examples of A, I should say. Yeah, and then we also verified whether Tm is we are assuming R is isomorphic to T, R is isomorphic to T in all the cases. RD, this one is isomorphism in all cases, and we verified whether that is going to be isomorphism, at least for some examples we verified, and it's true for some examples. I will tell you. We verified for this example, and then dimension 3. We computed cardinality of Atkin-Legner involution subgroup, and we computed rank, and then we computed modular degree, and we computed RD is isomorphic to Tm is true for all these examples. So it seems like R is isomorphic to T. If it's true, then we can remove that assumption what we assumed in our case.